Okay, students, I will be reviewing the halogen derivative consolidation exercise 1. Okay, so we have two questions here. So for the first question, you are given 3 halogenal compounds. You were told that they are dissolved in ethanol and then warmed with silver nitrate. So this is essentially what we call ethanolic silver nitrate. And the observations over here tells you how fast you observe the precipitate. So you notice that for the first test tube, it forms after 1 minute. So the AGI appear first, and then this is followed by the second test tube, that's 2 minutes. And then for the third test tube, no precipitate forms. You have to be a little bit careful when you look at the molecular formula. You might miss out the fact that this compound actually contains a sp2 carbon chlorine bond. Okay, so if I'm going to sketch this out, it will look something like this. So I have a CH2 here, okay, and then a CC double bond, because over here, right, this carbon is only bonded to one H and one Cl. Yeah, so if it contains only a single bond, right, then the valency of the carbon is incorrect, because that will mean that the two carbons are radicals, meaning they only contain 7 electrons each with unpaired radicals. So this is not possible. So that means that it must have a CC double bond. Yeah, so you just have to be a little bit careful when you look at the molecular formula. Do not straight away assume that it contains a sp3c chlorine bond. Okay, and of course, by telling you that no precipitate forms, it does give you a hint that the carbon chlorine bond is stronger than usual. So perhaps it may have partial double bond character, etc. Yeah. So 1A1 is pretty straightforward because they ask you to use the observations to explain the relative ease of hydrolysis of the 3 compounds. And the key focus here, which I often mention during tutorials, is that for nucleophilic substitution, the rate determining step involves the breaking of the C halogen bond. So this is very important. Okay, so the RRDS involves overcoming the CX bonds. How do we know that? Because regardless of whether is it SN1 or SN2, right, the substrate appears in the rate equation. So if you want a little bit of revision here, so we have for SN1, the rate equation is rate is equals to K concentration of the substrate, in this case Rx raised to the power 1, so first order. For SN2, the rate equation is rate is equals to K, you have Rx, and then you have the nucleophile, okay, raised to the power 1 each. So first order with respect to Rx, first order with respect to the nucleophile. So you notice that for all of them, right, the substrate appears in the rate determining step or in the rate equation. Yeah, so therefore it is crucial to be aware that the breaking of the C halogen bond, right, occurs in the RDS. So that means that the stronger the C halogen bond is, the more difficult it is to break, the slower the reaction. Yeah, and this is kind of like looking at how fast the precipitate is formed, and we are also looking at how fast the free halide is being released into the system, so that the ionic products of the silver halide exceeds its KSP, and that leads to the precipitation of the respective ionic halides. Okay, so in this case, because the CI bond is weaker, so when it is slowly being overcome, it releases enough iodide into the system as a free iodide, resulting in the ionic product of AgI to exceed its KSP, and that's why you observe pale yellow PPT. Yeah, so this is a link that I can share with you on how we can link up what we learned in solubility equilibrium to halogen derivatives. Okay, yeah. Then for part 2, describe the changes, if any, that you might observe when concentrated ammonia is separately added to the precipitate in test tubes 1 and 2. This is a pure recall question. Yeah, so you can easily check the second last page of your data booklet. Okay, so you'll notice that the information is provided there under the qualitative analysis test for anions. Yeah, so in this case, you can just copy down, or if not, if you could remember, silver iodide having the lowest KSP will not be able to dissolve in concentrated ammonia. Then for the case of silver bromide, in this case the cream PBT, it will dissolve in excess concentrated ammonia, giving a colorless solution. So remember that when you are trying to highlight whether the salts can dissolve in that particular medium or not, you have to tell us the before and after. Yeah, so in this case, cream PBT dissolve in excess equals ammonia, concentrated ammonia, giving a colorless solution. Yeah, so that's a gist of how you should be explaining a question like this. Okay, then we move on to B. For B, right, you have ethers, or some people pronounce it as ethers. Okay, organic compounds with a COC functional group. Yeah, so this particular functional group is not in your H2 curriculum, but you often see that it's being tested. Yeah, so it is an isomer of alcohol. So for example, this particular ether, okay, diethyl ether, right, is an isomer of butane 1-or, butane 2-or, etc. Okay, fully saturated as well. Okay, it can be made by reacting chloroethane with sodium ethoxide and ethanol. So this is the information being told to you. You might have some of these information when you are going through your lecture notes, or maybe during tutorials. Your respective tutors will have told you that. Yeah, so sodium ethoxide is made when I dissolved. There are a few ways to make it. I can actually dissolve sodium. I can put sodium into NEATS ethanol, okay, or I can simply introduce solid sodium hydroxide to NEAT ethanol. So both works. Okay, so I think the details is not very important over here. What you need to know is simply how to go about deciphering the information given to you by the question, and then answer the question accordingly. Okay, so for this particular reactions, if I can just highlight this particular part, you'll notice that this is the ethoxide, okay, and it's now being placed over here, so it replaces the Cl. Okay, so in this case, it's a form of nucleophilic substitution. So we were told that the ethoxide is one of the reactive species, and then they ask you to name and describe the mechanism of this reaction, show where relevant, etc. So this being a primary chloride, okay, or primary alkyl chloride, it is likely to undergo second order nucleophilic substitution. Yeah, so when you are trying to illustrate the mechanism, you should be drawing a second order nucleophilic substitution mechanism. So part 1 is pretty straightforward, so I'm just going to go through it quickly. So you're going to write the title, so nucleophilic substitution. You're going to spell everything out, and then you can put a bracket SN2 because you're trying to highlight that it is second order. Okay, I'm just going to use skeletal, which make my life easier. Yeah, so I have an ethoxide here. So remember to show the geometry around the CCl. So the simplest way is really what I've mentioned often in the tutorial. So I put a H here, I put a carbon, I put a Cl, then delta plus, delta minus, and then projecting into the plane is a H, projecting towards me is a CH3. Okay, so remember to draw your arrows in. So first arrow attack the electrophilic carbon, and then simultaneous breaking of the C chlorine bond. And then remember to draw out the transition states. So for SN2, it is mandatory. Okay, so I'm just going to put the H here, the H here, and then the projecting CH3, and then dot Cl. Okay, and then I put the transition state double dagger symbols, and then negative charge overall balanced. Okay, and then finally I'm going to draw out this O ethyl group, and then with a carbon here with a H projecting in a H, and then a CH3, and then plus Cl minus. Make sure you balance the overall material. So this is often being left out. Yeah, the Cl minus. So just take note of it. Okay, and of course I mentioned often in the tutorials that this leads to an inversion in stereochemistry. So if this is a cone and then this is an inverted cone. Okay, so there's an inversion in stereochemistry that you need to take note of. Yeah, so this is part 1, second order nucleophilic substitution. Okay, and then after that we have part 2, when methanol replaces ethanol as the solvent. the reaction between chloroethane and sodium ethoxide produce a mixture of this and this, suggests an explanation for the formation of this particular can I call it side product? Yeah, side product. Well, this is not too surprising because methanol is a source of O-methyl, okay, or methoxide nucleophile. So over here, right, what you need to highlight is that how is methoxide nucleophile being produced? Well, you are aware that let me see. Okay, in the presence of sodium ethoxide, I have O ethoxide or O ethyl, so O minus with a lone pair here. And then if I have methanol, so methanol looks like this with a CH3. Okay, and you notice that methanol has a protonic hydrogen similar to ethanol, so they will undergo acid-base neutralization. So this particular acid-base neutralization will produce the methoxide as the nucleophile, which will compete with the ethoxide to attack the electron-deficient carbon of chloroethane. Yeah, so in that case, I'm going to get a mixture of the two products. So that's not too surprising. Okay, yeah, so that will be the answer to part 2. Okay, then moving on to part C. A chemist wanted to react compound P. Okay, so P, you are given this particular molecular formula. Okay, just take note of it. This molecular formula C4H9Br. Okay, if you wish to calculate the degree of unsaturation, remember to treat this as to treat the Br as a H. So C4H10. So this is fully saturated. Okay, so because it fits the CnH to N plus 2. So this is a saturated bromoalkane, so saturated. So that means that there's no double bond or a ring. Okay, you react it with sodium ethoxide to make ether Q. Okay, so remember this, so I'm going to highlight the relevant parts. Okay, so this is the ethoxide. Okay, I'll check out where the ethoxide is, so it should be here. So this is the ethoxide over here. Yeah, so based on this particular reasoning, right, then I can say that, okay, this is the original moiety, okay, where the Br is being bonded to. Yeah, so if I'm going to look at this whole thing essentially is C4H9, okay. And then of course there should be a Br here. So since they ask you to suggest a structure for P, then this wouldn't be too difficult. So P should be like this. Okay, so this should be the structure of P, just based on inferring what we have over, because we are given the structure of ether Q, so we can easily infer what my P is likely to be. Okay, then over here, I was told that when P was reacted with sodium ethoxide in ethanol, right, the chemist obtained Q as the minor products, okay, and compound Q, which you notice C4H8, right? So if you try to calculate the degree of unsaturation, it is actually 1. Yeah, so that means that it is likely to contain a CC double bond, okay, or a ring. Yeah, you cannot confirm whether is it a CC double or a ring until you are given other information. But over here, it should be relatively obvious, because number one is P is a halogenoal bromoalkane. Okay, so that looks like this. So this is already drawn for you earlier on. And then in the presence of sodium ethoxide in ethanol, right, it is likely to be an elimination condition. Yeah, so if it's an elimination condition, then we can easily dismiss the fact that it is a ring. Yeah, so that is how you think about the situation, given the information, limited information given to you, right, provided to you, then you are able to go through a logical thought process and then come out with suitable response. Okay, yeah, so this is likely to be a elimination product. And then you were told that the conversion of P into R involved two-step mechanism. So again, if you remember the class exercise 2 I reviewed earlier on, I mentioned that in general there are 5 types of questions that can be asked in H2. Yeah, so this is an example of a guided mechanism. So you were told that the CBr bond in a molecule of P breaks heterolytically to give you a carbocation and a bromide. Yeah, so if I'm just going to use a very simple way to understand what's going on, right? So this is delta plus, delta minus. So heterolytic cleavage means it will break towards the Br, because the Br in this case is an electron sink. Okay, and then I'm going to end up with a carbocation with a plus charge plus Br minus. Okay, and then the ethoxide remove a hydrogen from the carbocation, causing heterolytic cleavage of a CH bond and the formation of a CC pi bond simultaneously. Okay, and then probably this carbocation, right? You notice that it has 3 equivalent methyl group, so maybe one of the H here is lost, and then this leads to a formation of a CC double bond. Okay, so you're going to end up with 2 methyl propenes. Okay, they require you to draw a displayed formula. Yeah, so I can easily draw the displayed formula like this. So C double bond C. Oops. Okay, H, and then C, and then H, okay, and then C, H. Yeah, so this will be the answer I'm going to write out for part 2. And then later on, you're told to use the information to draw out the two-step mechanism for the conversion of P into R. So this is a novel mechanism. Again, show relevant, etc. Right? So I draw a little bit for you here, but I did not use the display formula. I think it's fine. Okay, so perhaps I'm just going to continue from here. Yeah, so this is the first step. Okay, which is likely to be the slow step. Okay, then the second step, I'm going to have the carbocation over here, and then I'm just going to remove the proton or the hydrogen here with using the ethoxide, because I was told that ethoxide is the base, so I'm going to remove it, okay, via acid base neutralization. And then over here it mentioned very clearly heterolytic cleavage and the formation of a CC pi bond, so this must be broken towards the carbon bearing the positive charge. But of course you cannot point your arrow towards this carbon bearing the positive charge, because it leads to the formation of a pi bond. So the pi bond exists between carbon 1 and carbon 2. Yep, so in this case I form this plus ethanol. So remember to balance your equation. Okay, then for part 4, by considering your answer to D part 3 suggests why the reaction of P with sodium ethoxide gave more R than Q. So where is R? Okay, so Q is the ether, right? So Q is the ether over here. Then R is the alkene. So why do you think that it gives more R than Q? The question already stated that I'm going to get more R, which is more of the alkene products as compared to the nucleophilic substitution product. So this is the Q. The nucleophilic substitution product looks like this. Okay, so whether the fact is absolutely correct or it just fit the flow of the question, right? You do not need to question it as you are doing the question. Yeah, so basically now the question is telling you that, okay, over here I'm going to get more R. How would you answer it? And you know that this is the slow step. Okay, so the slow step actually produces the carbocation. Okay, so the carbocation is trigonal planar in geometry. So it has an electron deficient positively charged carbocationic center over at carbon number 1. So theoretically speaking, it might be easier for the nucleophile to approach the positively charged center by virtue of electrostatic attraction. Yeah, however, in terms of steric, it is actually easier to remove the proton nearer at the methyl site. So each of the methyl group, because it's being spread out, right, before the ethoxide can approach the carbocationic center, it will already approach the hydrogen over there. So in this case, you can also argue the fact that based on steric, right, it's actually easier for us to remove the proton of the methyl group. And at the same time, you can also highlight that elimination is entropy driven, because it produces an increase in number of moles of species. Yeah, so for in the course of the reaction, right, an elimination reaction in general produces more species. Yeah, so in terms of the Gibbs free energy changed, it releases more Gibbs free energy as compared to, say, an elimination, a substitution reaction. Yeah, so those are some of the factors you can actually provide as part of your explanation. Yeah. However, there's no hard and fast rule because this is likely to be just a 1-mark question. So and without learning additional stuff or H3 and beyond, etc., right, you might not be able to answer it in the clearest way. So I think a simple answer will do. So in terms of it's easier to actually remove the protonic hydrogen of the methyl group because it is less directly hinted. I think that answer might serve its purpose here. Okay. Then for part D, you were told about tetrahydrofuran. THF is a cyclic ether, and it's commonly used as a solvent. The THF can be made by intramolecular reaction. So you notice that over here I have 4-chloro-butane-1-ol. So I have a sodium over here. So THF structure will look like this. Of course, over here they did not tell you about how THF is likely to look like. But if I can just draw out 4-chloro-butane-1-ol, so Cl over here. So I have carbon 1, 2, 3, 4. And then I have OH over here. Okay, like this. So if I incorporate sodium in, then this is likely to be gone. Okay, then it will then have a lone pair over here with a negative charge and of course a Na plus, and then this will undergo an internal nucleophilic substitution. Oops, I think I drew one less carbon. This is a very common mistake by students and of course by teachers as well. 1, 2, 3, 4. Okay, and then O here. Okay, and then minus over here. Okay, and then this is delta plus, sorry, delta minus, delta plus. Then you undergo an internal nucleophilic substitution. Okay, and then I'm going to end up with a structure that looks like this. THF. Okay, so THF will look like this after it undergoes an internal SN2. And then you were told that it's cyclic, so there shouldn't be any CC double bond. Why a naked flame shouldn't be used to heat up the reaction mixture? This should be quite straightforward, and it's linked to one of your learning objectives. Yeah, so heating flammable substance such as the organic compound stated over here, right, and sodium with a naked flame may cause fire and risk an explosion in the lab. Yeah, so organic compounds, highly volatile, shouldn't be heated with naked flame. Yeah, any heating should be done in a water bath. Okay, so I hope that clears up some of the doubts. And to obtain THF as the major product, the initial concentration of 4-chloro-butane-1-ol has to be moderately low. Okay, the reason is this. Reaction is a probability game. Remember this. Yeah, so in the case of 4-chloro-butane-1-ol, right, if the concentration is relatively high, then an intermolecular SN2 might take place, which is eventually, right, will give rise to polymerization. Okay, so what do I mean by that? Okay, so if I'm just going to expand this particular structure, I'm not really expand, but I'm just going to draw it straight, right? So it will look like this: 2, 3, 4, O minus, right? Okay, now if the concentration of 4-chloro-butane-1-ol is moderately low, then the chance of it meeting another 4-chloro-butane-1-ol is relatively low as well. Yeah, so it is likely that maybe they are very far away, so it's not possible for this particular SN2 to take place. So for example, I have a Cl here, then I have 1, 2, 3, 4, then like this. So it's very unlikely for this to take place. Yeah, for you to meet another similar species as itself. Yeah, because if this were to take place, right, then I'm going to end up with polymerization, which is not something that I would want to obtain. And even if it's not polymerization, I'm going to end up with a dimer or a trimer like species, right, which defeats the purpose, because what I want is cyclic ether, which is THF in this case. I do not want unwanted side reaction like the one I've drawn below to take place. So in order for that to happen, I need to do it under a condition known as high dilution. Yeah, so this is a very specific term we use in research. It's called high dilution. So in a very diluted medium, high dilution. So if you want, you can take note of this as one of the chemistry terminology that you have learned in the course of the lesson. Okay, Yeah, so with that, we'll move on to question 2. Okay, so for question 2a, right, you were told that the ammonia reacts with iodoethane. Yeah, do take note is iodoethane, which is CH3CH2I, to form compound X, which is C2H7N. Yeah, so in case you're wondering how do I calculate the degree of unsaturation of nitrogen-based compound, right, you need to add 1 to the formula. So basically, the degree of unsaturation of this is equals to 2n plus 2, okay, which is 6, and then you need to artificially add 1 plus 1, and then minus of the number of hydrogen it has, which is 7, divided by 2, so it's 0. So this is saturated. So if it's saturated, it tells you that the reaction of ammonia with iodoethane to produce X, right? X is simply just a primary amine. It's a primary amine like this. Okay, you were told that a byproduct of the reaction is Y, with a whopping 8 carbon, okay, and 20 hydrogens. Okay, this may be a bit interesting if you just count how come suddenly the number of carbon bumps up to 8, right? Yeah, it will not be too surprising if you read the next paragraph. You were told that when lead nitrate is added to the aqueous solution of Y, right, you get a yellow PPT form almost instantaneously. So this actually tells us that in the system, right, or in the aqueous solution, there is free iodide ions. So free iodide ion means that the formula for Y, essentially you can look at it as C8H20N plus and then I minus. Yeah, so for this to happen, you probably will be aware that this is likely to be a quaternary ammonium salt. Yeah, quaternary ammonium salt. How do we end up with a quaternary ammonium salt when we begin with ammonia and iodoethane? Well, I mean, this wouldn't be too surprising because after the first reaction, meaning after ammonia reacted with iodoethane to give X, X in this case, right, being a primary amine, it will compete with ammonia as the nucleophile. Yeah, and it aminoethane, right, having a electron donating ethyl group, right, it is going to behave as a stronger nucleophile as compared to ammonia. So because it's going to behave as a stronger nucleophile as compared to ammonia, the competition is real, and I'm going to end up with a reaction that will look like this. So I'm going to draw out the NH2 here. I'm not going to show the 3D. I'm just going to show what is likely to happen. I delta plus delta minus. So this is going to undergo internal, or rather intermolecular SN2. Okay, and then I'm going to end up with this, and this. Okay, with a plus charge, and then of course the next step is with a I minus, of course, minus I minus. Then my ammonia, right, will then undergo a acid based. Oh, actually I should put my I minus the other side. My apologies. So this is minus I minus. Okay, this is minus NH4 plus, and then I'm going to end up with something like this with a H, and then this is actually a secondary amine. Secondary amine, and then the reaction will continue. So you can actually draw it in if you want. It will continue, and then I'm going to end up with a tertiary amine. Okay, and then after it will continue again with I. Yeah, so this time around the delta plus delta minus, right, there's no more proton to be lost. Okay, because there's no more proton to be lost, right, I'm going to end up with a quaternary ammonium salt with a plus, and then of course this whole thing, and then with a I minus on the outside. So this is an ionic compound. Okay, so when you dissolve this whole thing in water, right, the I minus is going to appear as a free iodide anion. So when that happens, then my ammonium salt is free floating. So because I have free iodide anion, when I add in lead nitrate, right, the ionic product of lead iodide is likely to exceed its KSP quite readily. So that's why it leads to the formation of lead iodide quite easily. And then this does give you a clue that this compound is some form of salts rather than the iodine is being bonded to one of the carbon or the nitrogen. Okay, yeah. Then I'm gonna move on to the next question, or next parts 2b. We have a reaction scheme involving 2-bromopentane. Okay, so you probably need to draw this out, or you do not need to, because I have 5 carbon. Okay, I have 5 carbon here. Okay, and then this is a Br, and then I'm going to get D. Okay, and then this is a reduction condition, or it's a catalytic reduction. Okay, so this reduction condition gives you this particular compound. So if I'm just going to count the number of carbon, so 1, 2, 3, 4, 5, 6. Now there are 6 carbon, and then a reduction condition gives me a primary amine. So therefore, my D is likely to be a cyano group. Okay, because after I reduce this, I'm going to end up with this particular compound, this particular primary amine, which fits the formula of the one given as the molecular as the condensed structure formula here. Yeah. So because of this, right, the reagents and conditions for step 1 will be the standard of what we have in our lecture notes lah. So ethanolic KCN heats. Yeah, so I'm going to expect a nucleophilic substitution of cyanide replacing the bromine. Okay, so basically this particular bromine will be replaced by CN. Okay, and then of course, yeah, given some clue here as well. The student investigated the kinetics of the conversion of 2-bromopentane into D. The rate of the equation is found to be like this, so it's clearly an SN2. Okay, so the sample used in the reaction contained only the following isomer of 2-bromopentane. There was an inversion of stereochemistry. Okay, so this is quite interesting because this question, right, specify the isomer being used. So therefore, when you are drawing the mechanism, right, you can only use this particular configuration. Okay, so in short, I mean just a short drawing or a short illustration. When the cyanide approaches the carbon, right, it must approach from the rear. Okay, so this is the rear, and then I break the bond. So therefore, right, when I'm drawing my products, because they asked me to draw a 3D structure of D produced, right, I can only draw it like this. Of course, there are other ways to draw it, but in terms of understanding, and in order for us to be aware that you understood the whole idea of inversion, right, you have to draw it in this manner so that we know that you are aware that this particular cone, okay, now it becomes the other way around. I mean, okay. Maybe this is not a very good way to put it. Wait, let me just, okay, so the cone actually is something like this. Okay, so now the cone is now like this. So there's some sort of like an inversion, but I don't think you can see it very clearly based on this drawing lah. So I think I'll just ignore it first. Okay, and then you're supposed to name and describe the mechanism for the conversion of 2-bromopentane into D, and then etc. This is a very standard question. You can use R to represent certain groups if you want, but I don't think as RC. Oh, you can represent this as RCH, BRCH3. I mean, we can do that if you want. Okay, so yeah. So again, the mechanism. Okay, so I'm just going to standardize the way I'm going to draw it because this is how it's being mentioned in the lecture notes. So I don't want to contradict. Okay, so delta plus, delta minus. So this is projecting in, and then this projecting in, and then I have another group, the CH3 projecting out. Okay, and then the cyanides, Cn minus. Okay, so I'm going to show the arrow in pink like this. It breaks. Okay, and of course again I'm going to draw in the transition states. Dot C R project in H, and then a CH3, and then dot BR. Okay, transition state double dagger negative, and then of course the inversion, which is the product. So I'm just going to draw it smaller. Okay, CH3 plus BR minus. Okay, Yeah, I'm not gonna explain further because we have already talked about it earlier on. So I think I'll just stop here as it is, and then straight away move on to part 4. Okay, suggest a structure for E. Yeah, so E is a hydrolysis product. Yeah, so because I'm going to expect D to be a cyano, right? So therefore, I'm going to expect the carboxylic acid to be like this. So this is a carboxylic acid, which is obtained from the hydrolysis of cyano compound D. Okay, yeah, then I'll move on to the next part. Part C. We have neopentyl bromide. It's an isomer of 2-bromopentane. Okay, so neopentyl, and then the kinetics of the reaction between this was investigated. So results is given here. Yep. So if I'm going to compare, say 1 and 3, okay. So when I increase the concentration of the bromoalkane by 4 times, the initial rate increased by 4 times. Okay. Not sure if this is surprising. Okay, so therefore, I'm going to expect the order of reaction to be first order with respect to the bromoalkane. Yep. Then over here, when I increase, okay, let me use a different color. When I increase the concentration of the bromoalkane by 3 times, and then I halve the concentration of the cyano, right? You notice that the relative rate increased by 3 times as well. Yeah, so therefore, right, from here I can highlight that the halving in the concentration of cyanide has no impact on the overall initial rate, or on the relative initial rate of the reaction. So therefore, the increase in the relative initial rate, right, is solely due to the tripling of the concentration of the bromoalkane. Yeah, so therefore I can conclude that it is 0 order with respect to cyanide. Yeah, so in this case, I just summarize it as a first order and 0 order. Okay, then for part 2, you will ask, is the mechanism of this reaction the same or different from the one you have described in B part 3? So it should be different because it is SN1. In this case, is first order nucleophilic substitution. And why is there a difference? Because in the rate determining step, it does not involve the cyanide as the nucleophile. Okay, so that will be the answer that we're going to give for part 2. And then over here, you were told that neopentyl bromide reacts with cyanide to produce compounds F and G. Okay, and analysis of the product mixture shows that the amount of G form is much greater than the amount of F form. Okay, and then suggest a structure for the 2 intermediates formed during this reaction. Okay, so the 2 intermediates form. So let's take a look at where the position of the CN is. The position of CN is here, position of CN is here. Yeah, so based on the clue earlier on, right, the whole reaction occurs via SN1. Okay, so if we simply look at the neopentyl bromide over here, I'm going to draw the skeletal out. So this is neopentyl bromide. Okay, wait, 1, 2, 3, 4. Yeah. Okay, then what's going to happen is that before F is formed, the carbocation is likely to look like this. Okay, so this is the carbocation leading to F. Okay, because the cyanides can then approach the primary carbocation to give F. Okay, then with the same thought process, right? Maybe I should use a different color in green. The carbocation leads to this is likely to be like this. Okay, it's a tertiary carbocation, and the cyanide will then attack the tertiary carbon to give rise to this. Okay, so if I need to number the carbon for greater clarity, that would be 1, 2, 3, 4, 5. Okay, then 1, 2, 3, 4, 5. Okay, yep. And then part 4 asks you, by considering the relative stability of the reaction intermediate, suggest why the amount of G is greater than the amount of F. Okay, the amount of G is greater than the amount of F is because G is a tertiary carbocation, whereas, or rather, the carbocation leading to G is a tertiary carbocation, whereas the carbocation leading to F is a primary carbocation. A tertiary carbocation is more stabilized, than a primary carbocation due to the presence of a greater number of electron donating alkyl groups. Yeah, so because of the greater stability of the tertiary carbocation, it is formed in greater amounts. Okay, and the greater amount being formed, right, will therefore leads to a greater probability of G being formed at the end of the day. Okay, so that will be the response I'm going to give for 2C part 4. And then for D, this compound is very reactive. Okay, so I'm going to again sketch this out. Okay, so I'm going to have a double bond here, and then this is how do I know that there's a double bond here? Because it's given here. Okay, and then a CH2, CH2, CH, and then a CH2 Br. Okay, it's very reactive towards hydrolysis, whereas this is not reactive at all. Okay, give 2 reasons. Okay, I'm going to highlight the words. They didn't bold it, so I'm going to highlight. Give 2 reasons why this is the case. Okay, so they wanted 2 reasonings. Okay, so what can we give? What kind of reasoning can we give? Okay, so number 1, it's the same kind of reasoning you will give why this is unreactive. I mean, okay, so it's just a very classic reasoning when we have this p orbitals here. Then for Br is using the 4p. So the 4p, 2p pi overlap, right, give it a partial double bond character. So that makes it resistance towards hydrolysis. Okay, so because it is resistance towards hydrolysis, right, then it will not be reactive towards the incoming nucleophile. Okay, yeah, remember that in the rate determining step of nucleophilic substitution, right, it is dependent on how readily the C halogen bond is being broken. So the more difficult it is to break, then the slower is the reaction. And of course, you can also argue from another angle that the pi system over here, right, will repel the incoming nucleophile. So that could be your second reason. Yeah, because it repels the incoming nucleophile, then that makes it even more difficult to undergo nucleophilic substitution. Okay, and then can we explain also from the perspective of this? Yeah, we can. We can say that this is a primary halogenal bromide or primary bromide. Yeah, so the rear of the C halogen bond is relatively unhindered. Yeah, so it can undergo SN2 easily. You can also highlight that it can undergo SN1 as well. Yeah, because the formation of a primary carbocation here in this case is favorable due to the fact that the primary carbocation is stabilized via resonance. Okay, or you can say that okay, so maybe let me just show this. There's a lone electron, and then this is the prime. This is the carbon with the empty p orbital. So you can say that the pi system over here, right, it will overlap side on. Yeah, so the pi electron cloud will delocalize into the positively charged empty p orbital. So it allows the positive charge to be spread out amongst the 3 carbon, stabilizing the carbocation. Yeah, so that is another reason you can give in this case. So you notice that there are a few ideas you can give, and it's really up to you to draft your answer in such a way that to fulfill what is required of you for the purpose of assessment. So I repeat, from the perspective of the alkene, the bromine alkene, right, I can highlight the partial double bond character. I can also highlight the pi bond, the presence of the pi system on the surface, right, will repel the incoming nucleophile. Okay, from the perspective of the primary bromides, I can highlight that the rear is relatively unhindered. So it makes nucleophilic. It makes the approach by the nucleophile from the rear relatively easy. I can also highlight that the formation of carbocation allows the carbocation to be stabilized, or rather the formation of the carbocation is favorable because the empty p orbital is conjugated. That's another term. It's conjugated with the CC pi system, so it allows the pi system, right, to overlap side on with the empty p orbital, and this causes the positive charge to be spread out almost equally amongst the 3 carbons. Yeah, so it leads to greater stability. Okay, so with that, we have come to the end of the review for consolidation exercise 1. I hope that you have gained some insights in doing this, and be ready to move on to the next topic.